Hello, everyone. So today we are in our 5th week already. Hopefully you had a enjoyable weekend. So we are moving on to chapter we're continuing on with the chapter 8 homework questions. Unfortunately, some of the chapter 8 homework questions didn't record or didn't save correctly, so you still have the video though. We're going to start on question 23. So if you can pull out your homework and go to question 23, we're going to begin where we left off at. After we get done with the homework today, we will go right into chapter 9. All right. Remember, just keep up with the due dates. This homework is going to be due, tomorrow. So you want to make sure that, you have your homework completed. Really should be no reason not to have it done. We've already done the first 22 questions. We have some questions left, but, we'll be able to complete those fairly quickly today. And I don't expect, you to memorize all these mechanisms. You do have your book, so please take advantage of, using your textbook when you go through, the different reaction synthetic steps. Today we're going to be looking at triple bonds after this homework. So, there's a lot going on. So, use your book as a resource. So question 23 gives us this. Double bond here, and we have bromine. So we have to decide, what are the expected products, and they give us a bunch of different options here. So you can see that the rings are fused in a trans position. So they're going to each be in the chair configuration. So they can't flip to the alternate chair configuration. So we're either going to have both axial or equatorial. So let me see. So yeah, we're going to select the first option. The first option gives them as both equatorial and then we have axial. So those would be the two positions that can form from this. So that's question 23. So all you had to do is select the correct answer. Question 24. It says they give us an alkene. I'm not going to draw the hydrogens, but there's a hydrogen right there. I'll just put it in. It's not that hard. It says draw the product of the bromination of this compound, including all expected stereoisomers. Okay. Use wedge and dash. So recall that, if we're going to attack a bromine, it's going to form here, then the bromine can either go here or it can go here. So that's why you're going to have two different products. So one product, we're going to have the bromine up, because if it attacks here, this bromine is going to come off right here. That's why I'm drawing it in that position. Then we'll have the bromine down. The hydrogen will come out, followed by this methyl group. So that's one product, and the other product would be, I'll call it Z. So if we have Z here, then the bromine is going to come up right there. That bromine down there. If you have a molecular model set, you can come back to this and kind of see, why this is. All right, so that's it. Let me see. Oh, this is the configuration of the alkene is Z. So we're going to press Z, because it is in this is in the Z configuration. It says characterize the product, select all that apply. So you're going to have an RR, you have an SS, you got racemic mixture. That's it. All right, so that's 24. Let me take a look at 25 then. So 25 is synthesis. That means we have to figure out what the starting material was. And they say, okay, we have bromine here, we have a bromination, and we have this. And this would be our starting material line. Yeah, let me write that better for you. And kind of similar, what's going on, you have that coming here. This bromine will be released. And once that bromine's released, it can attack. If it attacks on the downside, it's going to be released to this side right here. And that's what we see. Any questions so far? Let me see. So it's pretty similar. So let's see. It says draw the neutral. So I'm on 26 now. 26 says draw the neutral organic starting material that will react with bromine to form 2-bromomethyl tetrahydrofuran. And this will be the starting material. What was that? 26. Let me see. So that's what we'll have. This is your answer right here. Now, if you added bromine to it, you're going to form this cyclic complex right here. And then this lone, well, I shouldn't be doing this on the answer, but we'll just do it down here. It's a type of triangular complex. Then this will be released. Then we'll have a depronation. And then finally we'll be left with this. But you want to put this in for your answer. And this is going towards a more substituted, carbon right here. So it makes sense. All right, let's look at 27 then. 27 says, let me see. It's one of these 3D structures. It says, draw the major product form when the given epoxide reacts with aqueous acid. So my 3D structure needs a load. Okay. So you can't show the 3D structure here, but if you do, then you're going to get this. Let me just make sure I'm on the right one. Yeah, that's the right one. You're reacting this with aqueous acid, and this is what you get. So you're going to have a ring opening. That epoxide is going to open its ring because there's a lot of strain. Whenever you see something like this, there's a lot of strain here. So there's going to be some type of ring opening. And we do break that ring up. And we get the 2 alcohol groups. got someone in the chat. Okay, so someone wants me to go back to question 22. So let's go ahead and do that. So we did 27. Let me go back to 22. So question 22, and I know this would seem like we're gonna go out of order. We'll put 22 on here too, in case you're working on 27 still. So the curved arrow starts from so there's four options for 22. You're gonna select this one, and this one. First option says a curved arrow starts from the alkene pi bond and points to the bromine 1. A curved arrow starts from bromine bond and points to bromine 2. And a curved arrow starts from the lone pair of the bromine 1 and points to an alkene carbon. So what they're saying is, you have this right here, and they have BR1 and they call it BR2. It's the same thing, but they're calling this. The curved arrow starts from the alkene pi bond and goes here. A curved arrow starts from the bromine bond and comes here. A curved arrow from the lone pair of the bromine 1 and comes here. So then they're saying, draw the product. These are wedged arrows. And then it says select the curved arrow needed for step 2. Let me see. So step 2, this is step 1. So step 2, we'll draw this down here. You have 4 options again. We're going to select this one, this, and this one. So curved arrow starts from a bromine ion lone pair and points to a carbon on the bromonium ion. And a curved arrow starts on the bond between the carbon and bromine of the bromine and points to the bromine. So this is draw the final product. So you got this thing right out here in space, and this is going to come in here and attack, right? And then a curved arrow starts from the bond between the carbon and the bromine, and it's going to come here. So this is your first step, and step 2 would be here. And then we're going to form this. And this will be anti-addition. So that's 22. Remember not to select that one and only select the top 2 and leave these 2 blank. So we've done 27. Let me look at 28 now. Okay, you're welcome. So I'll just leave that up there for a minute. That way you can gather your thoughts with this one. All right, we'll go to 28 now. The 28 says predict the oxidation product of treating the alkene with your reagent shown. For any generated serocenters, specify the configuration by a wedge. So you have osmium tetraoxide. This will get rid of that double bond. It'll get rid of the double bond and put alcohols on there in a syn fashion. So that's what we'll draw. We'll draw the final product. That's why I said use your resources in your textbook, because I don't expect you to memorize all these reactions. we'll draw in syn addition what that does. And we have that. That's 28. All right, 28 is done. Let's go to 29. It says, show the curved arrow mechanism for the first step in the structure of cyclic intermediate formed when cyclopentene is treated with potassium permanganate. A Lewis structure for the permanganate ion is provided in the hint. Make sure to show all the non-bonding electron pairs and formal charges where necessary. Omit the potassium. The reason why they have potassium is because it's a counter ion. It's potassium permanganate, KMnO4. So MnO4 has a minus charge, so you need that potassium as a counter ion to counterbalance that charge. So they say you don't have to pay any attention to that counter ion. That's just one less thing that you have to put in then. So you have this. You can see where you have the formal charge now. That's why you have a -1, because 6 minus 7 equals -1. So this goes here. It's going to form a bond here. It's going to be released here. All right, so that's it. So that's 29. All right, so let's go to 30. 30 says, we have KMnO4. Show the stereochemistry. So we have a cyclic, 5-membered ring with an alkene on it, with the methyl group coming off. They want us to draw the 1s and the 2r product, and they want us. So we're going to have what the potassium permanganate is going to do is it's going to get rid of that alkene. We kind of seen kind of similar what's going to be happening right here, and you're going to form an alcohol group. Okay, and you're going to form it in the syn fashion. So you're going to let me go back to 30. So what we're going to do then is we're going to have 2 5-membered rings. And on one ring, you're going to draw them in the up position. And the other ring, you're going to draw them in the down position. Obviously, you got your methyl group here. They want you to show that hydrogen here. And on the other one, you're going to have the hydrogen down, and you'll have the methyl group down. So that's what's going on with that one. Any question on that one? And sometimes I'll wait a little bit because I know you guys are inputting. You know, I know everyone's putting in the answers in the achieve, so I want to give everyone the opportunity, you know, to make sure that they get the correct answer. All right, let's go on to 31 then. So 31 says predict the organic products in any order when the alkene shown is subject to an ozonolysis. So this ozonolysis is going to transform this into a aldehyde. Oh, I'm on 31. So this is product 1, product 2. I'm going to draw that a little better. We have this, and we have this. So you have product 1 and product 2. So ozonolysis breaks that double bond up. You know, smash that double bond. On this side, we're going to get this one, and on this side, we'll get this one. I think 30, that looks really similar. Just want to make sure. Oh yeah, so 32 is really similar to 31. we have this right here. We have another ozonolysis reaction. So we're going to form, again, we're going to bust this up and we're going to get two products. We're going to get one that's going to be the ketone, and we're going to get one that's an aldehyde. You can count 1, 2, 3. Now 1, 2. Here's your 2. Here's your 3. And those are 3 carbons, and this is 2 carbons. All right, so that's 32. Let's go to 33. So 33 says, draw the correct products in either order for the ozonolysis reaction. Again, we have another ozonolysis reaction. So you know what we're going to be doing. We're going to be busting up that double bond. And let's just, this is a phenyl group. It's just my shorthand for phenyl group. And we're going to be taking that out. So in one product, we're just going to have the ketone. The other product will have another ketone, but we'll have that phenyl group. So you can see I have 1, 2, 3 carbons here. That corresponds to the 3 carbons over here. The other one will have that 6-membered ring. That's that phenyl group, followed with our ketone in this fashion. You can see where this would have been right here. Oh, I'll draw that arrow for you a little better. All right, so hopefully, you're getting more comfortable with ozonolysis reactions. Ozonolysis just means we add ozone, which is O3. Remember, ozone is in resonance with each other, with itself. And what do we mean by resonance with ozone? Someone asked the question. We have this. It's in resonance with this, where that double bond can then shift. When that double bond shifts, you basically have something then where it's being shared amongst the other oxygen atom. And we draw it like that with the dotted line. In this case, this would be positive, this would be negative. Opposites thing over here. All right, so that's 33. Not too bad. We'll go on to 34 now. We have a couple more. It says, draw the structure of an 8-carbon alkene that would yield the following compound and no others after treatment with ozone. I have to refresh my screen. It's not showing up. Let me refresh it. Okay. So I see it now. We have that aldehyde. Okay, so we'll do that. So the starting compound. Oh. We have an 8-membered ring, so we have an octagon. 1, 2, 3. I got my octagon. I put, we can put it anywhere we want to, but that's it. So remember, this ozonolysis O3 will bust this out. Well, this will bust this open right here. If it busts it open, we do have a hydrogen coming off right here. So on one end, we'll have the hydrogen. 1, 2, 3, 4, 5, 6, 7. 8. 1, 2, 3, 4, 5, 6, 7. And then we'll have that. And I should have. Oh, I should have not. So I got my carbons numbered wrong, but this should be a 7-membered ring. I apologize for that. It's the same concepts. It's just a 7-membered ring. 1, 2, 3, 4, 5, 6, 7. All right. There we go. It busted there. This comes here. This one comes here. 1, 2, 3, 4, 5. There should be 7. Something like that. Now we got it. I don't claim to be an artist, so that's why I'm not the best at drawing these things. So we have a cycloheptene group, not hexane, not octane, cycloheptene. A 7-membered ring. We count 8 carbons here. Let me see. 1, 2, 3, 4, 5, 6, 7, 8. You count 8 carbons here. This would be your, 8th one. We have it all. So that's 34. All right, so let's go to 35. 35 is our last question. So it has our reactant. And how are we going to get to this right here? Well, you're going to add HBr and CH2, Cl2. That's your solvent. And you'll put that bromine in the Markovnikov place, the most substituted. Then it won't. So that's reagent R1. We'll call it R1. Then R2. We'll create a double bond. So there's a hydrogen here. If you use an ethoxide, remember this has this can do this can do this can do this. Then they want us to add then they want us to get this alcohol. with the bromine. So you can have, you're going to have to add some type of bromine to this, right? Here we're going to form some type of ring structure here. And then instead of bromine coming in, you'll have water coming in. And that water will kick here, and that bromine will kick off. That's how you get this. So we'll have to have water then. This is R3. So, unfortunately, I don't have any of the questions before 21. Like I said, there's been a lot of updates on our work computers. So what happens is our work computers just shut off without any notice. Well, very little notice to us. As you saw that one time I was in lecture. So I've noticed when I put my computer in sleep mode that I have to restart it. So, maybe that's another reason why we're getting new computers. Our computers are getting older. So we will all have new laptops in the near future. I think they're rolling them out this summer for some people and during the fall semester for others. So that's just the situation I'm in. So technical difficulties with older equipment. So does anyone have any questions on this? I'm gonna go ahead and save this. That way we can make sure that we at least have these questions. Please go ahead and open up chapter 9. I'm gonna pause the recording while you do that. All right, let's resume the recording. We'll take a break in about, we'll take a break at 11. So let's I'll share my screen. So we are on chapter 9. This study, chapter 9 is all about alkynes. That's your triple bond. So that's what we'll be studying. Alkynes are molecules that possess a carbon-carbon triple bond. So keep in mind that, the pen is not working. Let me get the pen. Keep in mind that a triple bond has more S character, 50% S. So, please keep that in mind when it comes to acidity and stability. So given the presence of pi bonds, alkynes are similar to alkenes in their ability. So this is double bond and their ability to act as a nucleophile. And remember, we saw this going on with bromine. So they can act in a similar way. Many of the addition reactions of alkenes also work on alkynes. They give you some examples here. Acetylene is the simplest alkyne. It is used in blowtorches and as a precursor for the synthesis of more complex alkynes, and more than 1,000 different alkyne natural products have been isolated. Alkynes are also used in birth control, and they show you this one right here. Ethinyl estradiol is the active ingredient in many birth control pills. You can see that alkyne group right here. So alkynes are named using the same procedure we use in chapter 4. So they go over some naming with alkynes. Identify the parent chain, which should include the alkyne. Assign a locant and prefix as necessary. Given the carbon-carbon triple bond, the lowest number possible. List the number of substituents before the parent name in alphabetical order. And the carbon-carbon triple bond locant is placed either just before the parent name or just before the ene suffix, sorry about that. So and YNE should be ein, not ene, because ene would be double bond. All right. So alkynes are named using the same procedure we used in chapter 4 to name alkanes. Identify the parent chain, which would also include the alkyne triple bond. They show you the ene, they show you the yne, octane, heptene. So, 1, 2, 3, 4, 5, 6, 7. This would be incorrect over here. We want to start this out at the lowest locant. To get that, we'd have to start on the left-hand side. So 1, 2, 3, 4. So we start this at the 2 position. So locant is 1 number, not 2, although the triple bond bridge is carbons 2 and 3. So the correct name for this would be 5,5,6-trimethyl-2-hepyne, or 5,5,6-trimethyl-hep-2-yne. Either one is fine. All right. So common names derived from acetylene are often used as well: methylacetylene, diisopropylacetylene, and phenylpropylacetylene. Alkynes are also classified as terminal or internal. So here we have a terminal alkyne, and here we have an internal. And acetylene is just this. It's used in blow torches for welding. And this would just be that's the common name, would be acetylene. It says recall that terminal alkynes have a lower pKa, more acidic, and we can base this based off of it has more S character. Here this is sp3, this is an sp2, this is an sp. Well, this would be 50. What would this be? 33. And this is 25. We can see that the pKa does go down, and it has to do with stability too. So acetylene is 19 pKa units more acidic than ethylene, which is 10 to the 19 times stronger. You just put a 10 here and you get 10 to the 19. So acetylene can be deprotonated by a strong base to form a conjugate base. So a strong base, water is a stronger base than acetylene, so you could think of this as water. You could think of this as some nitrogen group. Now we have this carbanion. I just wanted to see something real quick. So if we go back to page 113, we find the aerial, which is atom, resonance, induction, and orbital. So atom, which atom bears the charge? Resonance, are there any resonance effects that make one conjugate base more stable? Induction, are there any induction effects that stabilize one of the conjugate bases? And the orbital, in which orbital do we find the negative charge for each conjugate base? And I kind of already, talked about this. We had the sp3, which is less stable, sp2 and sp, and you can see the trend as you get more and more towards that s character, it becomes more stable. So acetylide ion is more stable because the lone pair occupies an sp orbital. I can't believe we're already in the 5th week already, to be honest with you. Next week is our last week. And the final exam is going to be comprehensive. Just to let everyone know. So a base's conjugate acid pKa must be greater than 25 for it to be able to depronate a terminal alkyne. We can see that, this is a stronger base right here. This is a weaker base. It's still depronated though. And they're just showing you the different methods of depronating this proton from this alkyne. So we're going to be, this reaction is going to proceed. If we just read this, it says a base's conjugate acid must be greater than 25. Okay, satisfy this for it to be able to depronate. We're not going to be able to depronate this as much right here because the base's conjugate acid is 15.7. It's a stronger acid, that means. So the weaker the acid, the stronger the base, so it's more likely to be depronating the terminal alkyne. So that strong base depronating that alkyne, and we get an alkynide ion. So sodium NH2 is often used as the base, but others can be used as well. NH2 is called sodium amide. I'll write that down for you. The common name is sodamide. What's your common name? I think this is a good time to take a break. So we'll come back at 11:10. Enjoy your break. If you have any questions, put them in the chat and I'll get back to them when we get back from the break. All right, we'll resume where we left off at. So let me go ahead and share my screen. We left off right here. We talked about, how acid strength increases from a single to a double to a triple bond. We also need a strong base to depronate that alkyne, and they give you a schematic that says these bases will depronate a terminal alkyne. You can see they're really strong bases. These bases will not pronate an alkyne. And they give you acid strength right here on this line. So like alkenes, alkynes can also be prepared by elimination. They need a dihalide to make an alkyne. So here we have an alkyl halide with a strong base. We can get this double bond, and then with another strong base, we can get rid of these two bromines and get the triple bond. And we do this through elimination. So here we form this alkene, the double bond. We form alkyne. It's very similar from what we've learned from the previous chapter, isn't it? So here we have E2 elimination. So this means it's a concerted reaction. So we go ahead and do this. This bromine leaves. So such eliminations usually occur via an E2. Geminal or vicinal dihalides can be used. Geminal means they're on the same carbon. Vicinal means they're right next to each other. And then we do another E2 reaction, and we have this as our leaving group when we form our alkene. Similar, we can do the same thing with a vicinal dihalide. Right, so excess equivalents of our sodium amide are used to shift the equilibrium toward the elimination products. So what do they mean by excess? Here we have two equivalents. We put in two equivalents in. So the first equivalent, will come here. Remove that. The second equivalent will take this one, and this will be gone. Then we can get rid of that hydrogen here and move this here, and we have alkynide ion. So aqueous workup is then needed to produce a neutral alkyne. So an aqueous workup with water, we protonate that, and we have our neutral alkyne. Okay, someone put something in the chat. Let me see. Yeah, so we can go ahead and do that after class. We can go back to that question. Let me see. Let me just take a look at it right now. Someone had a question regarding 29. Let me see. Yeah, we'll do that after class. That's fine. Overall, a terminal alkyne is prepared by treating the following dihalide with excess EX. They use shorthand just like I do. Sodium amide followed by water. So more than one equivalent is what that means. So are these geminal or vicinal? Well, this would be geminal. And you have a hydrogen here, a hydrogen here. You're going to have that base come in. Here goes one, and here goes the other one. But we only get this in 60%. Now, if you want to get rid of this stuff, this will add by syn addition. That means same side, you use a platinum catalyst, and they will get rid of this triple bond right here. So catalytic hydrogenation, we're reducing this triple bond to single bonds. Alkyne is converted to an alkane by addition of two equivalents of hydrogen. So the first addition produces a cis alkene via syn addition, which then undergoes addition to yield the alkane. So a deactivated or poison catalyst can be used to stop the reaction at the cis alkene without further reduction. So they say use this poison catalyst. In this case, they say the Lindlar's catalysts are common examples of a poison catalyst. So we're not going to proceed here. We're just going to stop right here. So it really depends on what you want to do as far as the products you want to create. So the poison catalyst catalyzes the first addition of the hydrogen, but not the second. So this step is catalyzed. This step is not catalyzed. So with the poison catalyst, you can see that we lower the activation energy. We form this, and then we're not going to go to the next step. So dissolving metal reduction reduces an alkyne to a transalkene using sodium metal and ammonia. So here's some different reactants to push this triple bond to a double bond. This reaction is stereoselective for anti-addition of hydrogen. And they give you an example of how the electron transfer works. So sodium has one electron. A single electron is transferred from the sodium atom to the alkyne, generating a radical anion intermediate. And here's your radical anion intermediate. We have a proton transfer. Another sodium will donate another electron. So a single electron is transferred from the sodium atom to the radical intermediate, generating an anion. Now instead of a radical, this is a radical. We have an anion. And that anion can get a proton from ammonia. So ammonia donates a proton to the anion, generating a transalkene. We can see that this is in the trans position right here. So I'm just going to leave that up because I know a lot of you are, seeing this mechanism for the first time. So dissolving metal reduction reduces an alkyne to a transalkene using sodium metal and ammonia. Step 1, the sodium atom transfers an electron to the alkyne, form a radical cation intermediate. We saw this. And note, they use the fishhook arrows to show a single electron, and this is what they mean by the fishhook. I'll just draw one. Now, two electrons would be this, but this would be one electron. Dissolving metal reduction reduces an alkyne to a transalkene using sodium metal and ammonia. So step 1, the paired electrons and the single electron adopt an anti-geometry. And the reason why they don't adopt like a syn geometry, there'd be electron repulsion right here. You can see that repulsion on the right-hand side. So we have the proton transfer from the ammonia, and then we have a single electron is transferred from the sodium atom to the radical intermediate, generating an anion. And the ammonium donates another proton to the anion, generating a transalkene. So no other reagents needed to reduce an alkyne to an alkane, a cis-alkene, or a trans-alkene. So if we want to stop it here, we're going to use this Lindlar's catalyst. But if we want to continue it on, then you just use some hydrogen platinum. You could have just went from here to here. Well, it shows you in the middle right here with this, you get the alkane. Now if we do this, we'll generate this, and obviously we can go here by using the platinum H2. These are just some mechanisms to keep in mind. So hydrohalogenation affords a Markovnikov addition of hydrogen and the X. And in this case, the X, is most likely going to be a chlorine or bromine to an alkyne, same as with an alkene. So this X is some type of halogen. Addition to an alkene, we have an addition to an alkyne. And excess HX affords a geminal dihalide. So geminal means the same carbon. We get to see that right here. I said if the mechanism was analogous to HX addition to an alkene, it would require the formation of a vinyl carbocation. But it says vinyl carbocations are extremely unstable, so this mechanism is unlikely. So this mechanism is unlikely. So kinetic data also suggests a different mechanism in play. Sometimes they don't know the exact mechanism. It's being researched still. So kinetic studies suggest that the rate law is first order with respect to the alkyne. You can see this is first order with respect to the alkyne, second order with respect to HX. If you add them, it'd be third order because 1 + 2 = third order overall. So the mechanism must be consistent with a molecular process. So here they have a proposed mechanism for this, where they have a transition state. So it's possible several competing mechanisms are occurring. So several competing mechanisms. So this is just one proposed mechanism out of several. So HBr, hydrogen bromide with peroxides, promotes an anti-Markovnikov addition, just like with alkenes. So remember, if we add this peroxide, we're going to put the Br on the side that is not as substituted. You can see that it puts it here. Otherwise, we'd be putting it here, wouldn't we? We're not doing that, so we get a mixture of the E and Z isomers here. This would be the Z, this would be the E. This only works with HBr, not with HCl or HI. And you only know that if you experimentally go in the lab and do this. So hydrohalogenation of alkynes and elimination of dihalides represents complementary reactions. We can see this right here. So if we have an excess HX, we form this dihalide, and we put, in this case, we put it on the geminal carbon. And if we want to go the other way, we just react it with excess sodium amide with ammonia and water, and we can regenerate our alkyne. So alkynes can also undergo acid-catalyzed Markovnikov hydration. The process is generally catalyzed with mercury sulfate to compensate for the slow reaction rate that results from the formation of vinylic carbocations. Here they show us an enol, and we can go to the ketone. But the alkyne attacks the mercury cation to form the mercurium ion intermediate. We've seen this before. This can come in here. There's a carbocation. It can be deprotonated. And we have this right here. And that's an enol intermediate. So a proton then replaces the mercury 2+ to form the enol intermediate. So here's your enol intermediate right here. It shows the mechanism, how it's going to go ahead and do that. This alkene takes its proton from this H3O+. This is going to come here. The mercury is going to go away. And we have our enol. So the enol that tautomerizes to the ketone, the process called a keto-enol tautomerization. So let's just think about this. The enol and the ketone are tautomers. If one another equilibrium generally favors the ketone. And that's due to the, it's a more stable, the ketone is more stable than the enol. But to get to the, you can go either or. So this, this could be protonated here. This can come here like that. That would be released. Obviously, the proton will be here. That can come down like that. And this is going to be taken out. Tautomers are constitutional isomers, but they have the proton in a different position. So here we have the proton here. Here we'd have it right here. And we can even count this. So how many carbons do you have? 1, 2, 3 carbons, 1 oxygen, and let me see, we have 6 hydrogens. Here we have 3 carbons, 1 oxygen, 3, 2, 5, 6 hydrogens. So they are constitutional isomers, but they just have the hydrogen at a different position. And they're switching back and forth. Now, the question, okay, I want to get rid of some of this stuff, and this will be the last slide we do today because I do have some questions, but I just wanted to show you. So let's just say we have like H3O+ here, right? So we can take off a proton. So when we do that, we have this right here. Obviously, there's going to be a positive charge here because 6 minus 5 equals +1. Then this double bond can come here. Well, the double bond can break itself off right here. And that's how we're going to get to here. Now, once we are here, think about this. We have an elimination then. Well, we don't have elimination. Sorry about that. Shouldn't call elimination. We have some type of base that can come in here, take this proton, and move this right here. And that's how you get to the enol form. So we're taking a proton off here, forming that double bond, we get rid of that formal charge. It's not elimination, because if elimination would be getting rid of the OH group. So hopefully that shows you how to go back from the ketones to the enol, because they didn't show it to you. They don't show that. So I wanted to go ahead and show that. All right, so that's it for today. Enjoy the rest of your day. I'll see you tomorrow. If you have any questions, please stay, and I will answer the questions, in the order they were received.